like to thank our organizer for this invitation, because you know that audience are really expert on operator algebra. Today I will talk about Atiyah-Schmid formula and automorphic representation. So Atiyah-Schmid formula is some stuff connecting operator algebra and representation theory. And today I will also enhance this connection to automorphic representation. And automorphic representation is one side of the so-called Langlands program. And that program is highly connected to quantum field theory, but I will not cover that connection today. Okay, so let's move on. So here is the outline of my talk. First, I will have a very quick review on a subject called correspondence, mainly the Langlands correspondence. So I will just use one page of slides to have a review of Langlands correspondence. And then I will talk about Jacques Langlands correspondence. So that is somehow a byproduct of the Langlands correspondence. Langlands correspondence is unknown, it's still conjectural, but Jacques Langlands correspondence is completely known. Then I will have a review of the Atiyah-Schmid formula. First, what is the origin of that? Second, what cases that formula does not work? I will provide a solution. I will generalize the original Atiyah-Schmid formula to work for some general cases. Then I will prove some result called local global compatibility. So it will not take long. And then I will state my main result. Okay, now here is a one-sentence summary of the main result. I will prove that von Neumann algebra will provide some arithmetic invariant of the Jacques-Langlands correspondence. Okay. So here is the summary of Langlands correspondence. Suppose G is just a reductive group over rational field. When we talk about reductive group, we can always have GLN in our mind. And G over Adele is defined to be the group elements in the product group such that the local component is in group over p-adic integers almost everywhere. And if we are given a irreducible representation of this Adele group, of this group, and the irreducible representation of that, it's known that it can be decomposed as a tensor product of the group over local fields. So here is the same group, but with over the local field. And by automorphic representation, we mean all the irreducible representation appeared in the L2 space of this quotient. And a very natural question is, what is the decomposition of this L2 space? So there are mainly three segments. First one is the most important one. We usually call them Caspidal automorphic representations. They form a direct sum. Second is somehow elementary, so they are only factors. Third one is the direct integral of existence series. And we will focus on the first term here, the so-called Caspidal automorphic representations. Let LG defined to be the Langlands L group of G. I will not give you the precise definition. It's just related to the root theory and Lie theory. So, but I will provide an example. The Langlands L group of GLN is just GLN over complex field. And the global Langlands conjecture denoted by GLC, the statement is that there is somehow a correspondence between Caspidal automorphic representation of the Adelic group to the homomorphism of the absolute Galois group to the Langlands L group of G. And here is another version, it's a local Langlands conjecture. There is a conjectural correspondence between admissible representation of the group over p-adic field. You can also replace the admissible by unitary. is fine. So the correspondence between the representations of and also homomorphism between two groups. LG is also the Langlands L group, and W sub P is usually called Weil group, which is a group related to the absolute scalar group of p-adic field. So we should only have two things in our mind: the global and local Langlands conjecture. Both of them are only known in a very special cases. Yes. Okay, so that is just restatement of the global Langlands conjecture. Suppose H is an inner form of G. So by an inner form, we mean that if we suppose they are both defined over field F, they are not isomorphic over F, but they are isomorphic over the algebraic closure of F. So that means if we just consider the rational field, they are not isomorphic, but they are isomorphic over the closure of rational field. In the same way, they are also isomorphic as their L group are isomorphic because the L groups are defined over complex field, which is algebraically closed. Here's a typical example of inner form. Let's start with the Hamilton quadratic algebra over F. F can be taken to be real field, p-adic field, or a rational field, or any field you want. So H sub F is an F algebra of 4-dimensional with 4 generators, 1 IGK subject to these relations. If you look at local version of this algebra, I mean the complex point of this algebra, it is exactly 2x2 matrix. But the real point is not 2x2 matrix. And if you look at the p-adic field, they are 2x2 matrix if and only if P is not 2. So that is to say there is some arithmetic information inside for this inner form. And globally, it's over rationals is not 2x2 matrix. So that is to see if you consider the multiplicative group of H, it is GL2 if P is not true or real. And in this way, we can also define the ramification side of H course, which is defined to be the primes. That the algebra H, the multiplicative group H, is not isomorphic to GL2. Okay, so for this algebra, it's just true and real. Okay, let's move on. So here we go back to the specific case of the H, which is an inner form of GLN. They have the same L group. And let's go back to this conjectural correspondence. If we just look at the right-hand side, they have the same L group because LH and LG are isomorphic, so they have the same right-hand side. So there should be some, so the right-hand side are isomorphic, so they have some correspondence on the left-hand side. And the correspondence on the left-hand side is exactly the proved Jacques-Langlands correspondence. Here's the statement for GLN. There is a correspondence between automorphic representations of H and G, and also a local representations between the unitary representations of H and G over p-adic field, such that if the global correspondence sends the tensor product to another one, it's matched locally.
Sorry, just to understand. So we know about, well, so here we know that the right-hand side is the same.
Yeah,
right?
and the two they are conjectural.
Conjectural. So
but the left-hand side is known.
Left-hand. Okay.
Yeah.
Okay. So, but this from this Jacques-Langlands. So this is proven or this is a conjecture? I didn't.
Jacques-Langlands is proven.
It's proven. Okay. Okay. So okay, and therefore that gives you some indication for how. So how does it give you some leeway in or help to prove Langlands conjecture or?
Yeah.
Okay.
Yeah. Yeah, this usually is based on the same tool called trace formula. Okay, so let's move on. So that is the statement of Jacques-Quislon correspondence for GLN. Here is my approach, just the von Neumann algebra approach. You know that Jacques-Quislon lens and there is actually a pairing between Caspito automorphic representations of different group H and G. So Jacques-Quislon lens sends a tensor product to another tensor product of representations, which are a correspondence between G A module and H A module. Here's a Del ring. And by GQ and HQ, they are just subgroup of the bigger group. So it also gives us a pairing of module over the group over rational. And also, I can prove that it's a module. Since it's a pairing of the module over the group von Neumann algebra of these two discrete group. So by L and L of G and L of H, I mean the group von Neumann algebra of GQ and HQ. So suppose gamma and gamma prime are certain arithmetic group. So you can just have projective GLN over rationals in your mind. Here's the goal. So if Jacques-Quislon sends pi prime to pi, I will prove that the dimension, actually that's the von Neumann dimension over these two different representations over the two different arithmetic groups are identical.
Topology are using groups, GL.
Well, you mean for discrete group?
Find von Neumann, so the group.
For discrete group, there's only the discrete topology.
Yeah, everything.
Yeah.
Okay.
But for Lie groups or p-adic groups, there are some natural topology.
From p-adic, also adelic, you have some natural topology.
Yeah, they have some natural topology.
And you use this to define.
Yeah. Okay. So here's go. I'll prove that if the von Neumann dimension is kind of invariant under Jacques-Quislon lens correspondence. Okay, so here we that's something much easier. So we'll have a quick review of the Atiyah-Schmid formula. Gamma here is not any arithmetic group. We can just assume it's a discrete countable group. You can have GL2 over integers in your mind. And let's consider the left regular representation of gamma on the L2 space of itself. The left group von Neumann algebra is defined to be the weak operator closure of the image of this representation. And in the same way, we can define the right group von Neumann algebra. The commutant. Let's talk about the commutant. We can show that the commutant of the right group von Neumann algebra is exactly the right one, and the commutant of the right one is the left one. There's a trace on both group von Neumann algebra. The trace is given by this inner product. I think it's out of problem. I can use. Probably I'm not face.
Yeah.
Okay. Yeah. So we have choice on the two group von Neumann algebra. Suppose pi h is a module over this group von Neumann algebra. There exists equivalent isometry over this group von Neumann algebra in this box, which is isometry noted by U since H to the tensor product. And that isometry entertains the action of L gamma. If we just consider the composition of U and U star, we know that this composition locates in the commutant here. And on this commutant, we have also a choice. So this commutant is isomorphic to the right group from algebra, considering the all-bounded linear operator over L2 of G. Actually, we can replace this Hilbert space by any infinite dimensional Hilbert space. And we have two trees on this tensor product. And the gamma dimension, or you call it von Neumann dimension, is defined to be the tensor trees of this composition. And this definition does not depend on your particular choice of the isometry U. So that is well defined. And if the group gamma has some so-called ICC property, this dimension give you the isomorphism class. I mean, if they have the same von Neumann dimension, they are isomorphic as module over the group von Neumann algebra. Okay, let's move on to the Atiyah-Schmid formula. Suppose G over real is a semi-simple Lie group. You can have SLN over real in your mind. And we take G's over integers to be the lattice inside. And here's the statement. Suppose G is semi-simple real Lie group and gamma is a lattice inside. Let pi be a discrete series. I will give you the precise definition later. The Atiyah-Schmid formula says that the moment dimension of H is exactly the volume of the quotient space times the degree of pi. I will define the degree of pi later on this page. First, for this representation pi of H, we first consider its matrix coefficient defined by this inner product. We call pi H a discrete series representation if this metric coefficient is in the L2 space for some, hence for all two vector u and v, or equivalently is a sub-representation of the L2 space, the regular representation. And here is the definition or the lemma for the formal degree. There's a constant which is non-negative real, denoted by degree of pi, such that we have this equation, the degree times the, here we have the inner product on L2 of G. On the right-hand side, you have the product of two inner products for the underlying space H pi. And this constant degree of pi depends on your choice of Haar measure. So that is a parameter attached to the discrete series. Okay, let's continue. We should keep in our mind there's some comparison between semi-simple groups and the reductive groups. For semi-simple groups, their center are always finite, so we have SLN. And for reductive group, we usually take GLN as a typical example. And for reductive group, its center is usually not compact or finite. For example, the center of GLN over any field F is the multiplicative group of F. And here are two obstacles to extend the Atiyah-Schmid formula. First, for reductive group, it has no discrete series at all. Suppose H is a discrete series. And we take two vector UV inside. And we consider the inner product over H. Because for discrete series, it can be embedded in the L2 space of G. So we have this formula and inner integral diverge. So let us see, discrete series does not exist for a general reductive group. And here's the second obstacle to apply a Atiyah-Schmid formula for a reductive group. There are no arithmetic lattice. So here is an example. If you just consider GL2 over real and GL2 over integers and consider its quotient space, the Haar measure of this quotient space is infinite. It's always infinite. Well, for semi-simple group, SL2, the quotient space is always of finite higher matter. Okay, there are two obstacles, and I will solve both of them later.
Can I make a question?
Yeah.
So when you say this is H should be contained in L2 of G, is up,
We suppose it's a discrete series.
but it's up to some multiplicity.
Yeah.
So it's not strictly. So for example, if G is compact,
When G is compact,
then
I will.
just a multiple of an irreducible representation
Yeah.
be discrete.
Yeah. Up to some multiplicity, right? You know that a Lie group has a discrete series if and only if its rank is the same as the rank of its maximal compact subgroup K. So here K is the maximal compact subgroup. But a Lie group, or generally just a locally compact unimodular group, we usually have tempered limitations. Tempered limitations are generalization of discrete series, and they always exist. So here's definition of the proposition for tempered representations. Representation pi acting on H is called a tempered representation if the metric coefficient is in L2 plus epsilon over G for any positive epsilon, or pi is in the support of a planetary mirror of G, denoted by nu G. And I will also introduce the planetary mirror on the next page. And or equivalently, H is weakly contained, not strictly contained in the L2 space of G. I have to mention just, as I mentioned before, discrete series are a typical example of tempered representation, but they are not all of them. Here is the classical non-abelian Fourier transform defined on locally compact unimodular group. And based on this Fourier transform, here's the planetary mirror or planetary theorem. So the Fourier transform sends L2 functions on G to the right-hand side, which is a direct integral of tensor product. And less isomorphism intertwines with two actions of G. I mean the left regular orientation and also right regular orientation of G. So on left-hand side, we have two actions of G. On the right-hand side, we also have two actions of G. First on the first vector and the second action on the second vector. And that is the classical Fourier transform defined for non-abelian group. And in that way, discrete series can be defined in another way. That are the irreducible representations, such that the planetary matter of this single representation is positive. And in this case, the planetary matter of this single representation is exactly the so-called formal degree I defined on the previous page. And here's the caution: both formal degree and planetary matter depend on your choice of higher matter. Here we take a subset of irreducible representation of G. And we take Hx to be the direct integral of all irreducible representations appeared in X. So that is naturally a module over G. So here's the first generalization I proved 3 years ago. The Monument dimension of H sub X is exactly the volume of the quotient space times the planetary matter of X. And if we take X to be a single discrete series representation, in this case, the planetary matter is exactly the formal degree, and this formula reduced to the original Atiyah-Schmid formula. So in that way, we have already solved the obstacle that it does not for tempered representation. In this way, we involved tempered representation. Okay, then we can handle the second one. In some case, the arithmetic group, I mean the group over integers, is not a lattice. The quotient space has infinite covolume. But we know that if G is semi-simple, the quotient space always has finite volume. And here's some fact. Semi-simple groups are contained in reductive groups, and often are unimodular. So we needn't to worry about the modular function. They are always unimodular. And for reductive group, we expect to have some semi-simple group from them. So here's the typical construction. We take G adjoint to be the group G quotient by its center. We usually call this the quotient, the semi-simple quotient group of the reductive group G. So that group is semi-simple, and if we just consider this semi-simple group, its integral points is a lattice. And here's an example. If we just take G to be the typical GLN and the adjoint quotient to be the projective GLN, we have the this volume is infinite, but this volume is finite. So that is to say how we get a semi-simple group from a reductive one. We just quotient it by the center. So now we have some semi-simple group from a reductive group, but this behavior destroys rotation. Suppose we have a irreducible rotation of G, then that should be related to irreducible rotation of the semi-simple quotient, but it's only a projective rotation because we quotient it by center. Let us see if we take two elements from the quotient group. The irreducible rotation is only a homomorphism up to a scalar. So for some two cocycle in the second cohomology. So we still have a rotation, but it's projective one. But we can also do that for the Atiyah-Schmid formula. We also go back to a very general setting. G is only a unimodular group. And omega is a fixed two cocycle in the second cohomology with coefficient in the circle. And by the omega projective rotation, we mean all the representations subject to this relation. So they are homomorphism up to this two cocycle. And a typical example is the left regular rotation, which has the two cocycle involved. We call this the omega left regular rotation. It's defined by this formula. And also we have the right omega projective regular rotation, defined the second formula. And in this way, we can define the omega twisted group from Newman algebra. I denote by L gamma omega and R gamma omega. And in the similar way, we can define the omega twisted gamma dimension. I denote here the two notation in the box. Now we can treat this as either as a dimension over Newman algebra or over the group itself. Are there any questions so far? Okay. Let's move on. Oh, there's a projective version of the planetary mirror. If you just consider the L2 space of G and we will not consider the left or right regular rotation, this time we consider the omega twisted left and right regular rotation. We still have the planetary mirror, but it's a twisted version. We have the two cocycle omega involved. And let's isomorphism intertwine with the twisted left or right regular rotation and also the two actions here. So pi conjugate are omega twisted rotation. And now we also take X to be a subset of the twisted unitary dual of G. And we suppose its planetary mirror is finite. We also denote HX to be the direct integral of all the irreducible rotation appeared in this twisted dual. And Hx sub x is a module over the twisted group von Neumann algebra. So we can consider its dimension over this von Neumann algebra. So here's the second generalization I proved last year. The twisted von Neumann dimension of Hx is exactly the volume of this quotient space. But this times we times this by the twisted planetary mirror of X. And how this reduced to the Atiyah-Schmid formula? I will talk about in next page. Now we go back to another approach. We suppose we start with X nu to be a mirror space. And we can define the gamma density. This definition is not created by myself. You can find this from several resources. Suppose there is a real number, positive real number, capital C, and Hx is a field of Hilbert space over X. I mean, they are indexed by X. And for any subset Y in X, Hy, the direct integral of Hilbert space appeared in Y, is a L gamma module, or the module over the twisted group von Neumann algebra. Second property is that its von Neumann dimension is proportional to the planetary mirror of Y. If both we have these two conditions, we call this the gamma density of Hx, which is C times the planetary density of X, the lowercase x.
Also with gamma here.
Gamma is
Even X, but
yeah. So Hx. So I forgot to mention that Hx. Oh, here. I don't forgot to mention. So H sub y is a module over L gamma.
but gamma is a discrete group
Yes.
on the space of the measure space.
No,
No,
no assumption on that. We just assume that Hy is a module over H
Okay.
gamma for any y.
gamma is a discrete group.
Yeah. Gamma is always a discrete group. And if we have these two conditions, we call this gamma density. And we also have the twisted version of gamma density. And because we have proved this, that is second generalization I did in the previous page. Because of this equation, it's just a corollary that the density of pi is just the volume of the quotient space times the planetary density of pi. So I think there's the same thing. You just take the differential. You can get this. And here, if pi is a discrete series and the 2 cocycle omega is trivial, it is the original Atiyah-Schmid formula. Are there any questions so far? That is our story I prepared for Atiyah-Schmid formula.
So that's just, so in point 1 of your definition of the gamma density, you're not demanding that the H-axis.
We do not assume Hx is,
Assume that the integrated things.
yeah, we only assume the integral is a module. Okay, so now that's the local global compatibility. So now we go back to some Langland stuff. H is an inner form of GLN over rational. And in this way, the local group, I mean H over local field, is also inner form of GLN over rational. Here I should mention Q sub infinity is just a real field. And Jacques-Langland send tensor product to another tensor product, and it's compatible with the local Jacques-Langland. And here's the statement of Jacques-Langland, just send irreducible rotation of H to irreducible rotation of G. And we may start with mu G and mu H to be two hard mirror on two different groups. And they give us the planetary mirror of on the irreducible dual of these two different groups. And we know that the hard mirror determine the planetary mirror. So if we multiply the hard mirror by constant C, we should divide the planetary mirror by these constants. And here's a theorem for local Jacques-Langlands proved by Albert and Playman. They prove that Jacquesson lines preserve planetary matter up to a constant, denoted by capital C. This constant depends on your choice of two hard matter at the beginning. And that holds for any temporal limitation. So in one word, the local Jacquesson lines preserve planetary matter up to some constant given by the hard matter. Okay, now let's go back to the real group. For the real group, we have some gamma real. Gamma sub-real is some group related to the absolute Galois group for real. So that is the abelian group of two elements. Let's phi G to be the L parameter of G. So they are defined to be certain homomorphism up to some equivalence. And here's the completely known Langlands conjecture for real group. It was the first known Langlands conjecture proved by himself in 1970s. So there's the reducible limitation can be put into a partition index by the L parameters. And if G is quasi-split and G prime is an inner form of G, there's embedding send the L parameters of G prime to G. And we denote the planetary matter of the L parameter to be the sum of all the planetary matter of the irreducible limitation appeared here in the L packet. So probably this is not so clear, but we can reduce down to a special case. Just a proof that this embedding preserve planetary matter. So for the local Jacquesson lines correspondence, it also preserves the planetary matter of real groups. So this case is much easier to prove because it's just established by Langlands result. So in one word, the real Jacquesson lines correspondence always preserve the planetary matter, also up to the constant determined by the hard matter. Okay, so that's a summary. We have local Jacquesson lines correspondence of GLN over real or over p-adic field. And for GLN over p-adic field and its inner form, we know is the Jacquesson lines correspondence preserve the planetary matter. And for general real group, the Langlands correspondence gives us this property, and also as a byproduct, the real Jacquesson lines correspondence always preserve the real planetary matter. So we can always normalize the hard matter we pick at the very beginning to make the constant to be 1. We can always do that, but there's a big one big restriction. So suppose we have already picked our desired hard matter for all the local groups and consider its product. Its product gives us the hard matter on the adelic group. And this product is a hard matter on the other adelic group. But these two adelic groups have their own natural hard matter. They are called Tamagama matter. And I'll give you a definition of Tamagama matter. Suppose G is GLN. So it's as a Q variety, the dimension is n squared. So the left invariant differential form of the top degree n squared is one-dimensional. We take omega to be such a left differential form. And we consider its localization. It's also a left invariant differential form of the top degree on the local groups. And if we consider this notation, it gives us a hard matter on the adelic group. And this does not depend on your choice of omega at the beginning. So let me explain. If you take another omega prime, which is lambda times omega, we have omega prime at p is the p-adic valuation of lambda times the old omega p. But the product of the p-adic valuation of lambda is 1. So the Tamagama matter is does not depend on your particular choice of differential form. So here It's a well-known conjecture which is proved. So the Tamagawa measure of a semi-simple group, semi-simple simply contact group, I mean the quotient space of a Dolly group by its rational group is 1. So why? That is another explanation why Tamagawa measure is some natural Haar measure. So here let me restate the restriction. We can feel free to normalize the constant, which is preserved by the crystalline lines, but we have to make this compatible with the Tamagawa measure. So we start with G to be GLN over rational, and G prime is the inner form. And here's the lemma I proved last year. For each P, there exists Haar measure, mu P and mu P prime on these two groups. I mean G over p-adic field and H over G prime over p-adic field. They are inner forms, and which determine the planetary measure respectively on the two unitary dual, such that the Jacques-Crystalline lines correspondence preserve the planetary measure, and we have no constant here. It's strictly preserved. That's not up to any constant. The constant is 1 for this particular choice of Haar measure, and also the product are exactly the Tamagawa measure. So that is to say the preservation of planetary measure of local groups is compatible with the Tamagawa measure. And it holds for number field, while this lemma is just stated for rational field. Okay, now it's ready to mention my main result. H is also an inner form of GLN over rationals. And H over p-adic field is also an inner form of the GLN over p-adic field. And there is a finite ramification of H of primes. And here's definition. For the primes inside this side, H over QP is not isomorphic to GLN, but it's isomorphic to GLNP over D. D here is a central division algebra of some larger dimension, not of dimension 1. So for the primes in the ramification side, the two local groups are neither isomorphic, but that's a finite set of primes. But for P not in this finite set of primes, they are all isomorphic. So recall that Jacques-Crystalline lines sends tensor product to tensor product that is compatible with the local Jacques-Crystalline lines. Let us to see for P in the ramification side, it is the local Jacques-Crystalline lines. But for P not in the ramification side, the two local groups are isomorphic. So in this case, the local Jacques-Crystalline lines is just the identical map. Okay, so now let's move on. We go back to this global Jacques-Crystalline line since tensor product to another tensor product. So both these two tensor products are representation of a Dolly group. We take a finite side of primes, include infinite one. And so here the Q sub infinity is real. And we consider the S groups, which are nothing but the component, the product over all primes appeared in S. It's a finite product of local groups. So we have HS and GS to be two S groups. And we can consider the semi-simple quotient, the adjoint one. So we just quotient everything by center. Now we have two semi-simple groups. And we consider S integers. S integer is just adjoint integers over 1 over these primes. So suppose example, Z over infinite 3 is the adjoint 1/3. And as arithmetic subgroups or groups is just defined to be the adjoint group over S integers. We have gamma sub S and dirt sub S, and they are lattice in the S groups, I mean the semi-simple S groups. So you know that we can consider the S component of this Jacques-Crystalline lines. It's not a global one, but a semi-global one. We have finite product of local groups. So they are repetition of HS and also of GS. And also there are projective representations of the joint quotient, semi-simple quotient. So there are also projective representation of the two as arithmetic groups, gamma s and delta s here. Okay, so now, so these the Jacques-Coetzee S component Jacques-Coetzee sends S product to S product. It sends projective representation of gamma s to projective representation of delta s. And it also sends the group polynomial algebra of these two groups to the other one. So here's the main theorem I prepared for today. For any tempered representation pi and pi prime of G adelic and H adelic respectively, such that they are matched by the global Jacques-Coetzee correspondence. We have the gamma density, or you can say that's gamma dimension of this S component of this tensor product are identical with respect to the two different arithmetic groups for any sect containing the ramification sign. So let us to say the gamma density or the monument density or monument dimension provide the invariant under the global Jacques-Coetzee correspondence. There are two remarks. First thing, it also holds for any other number field, but I state here for rational field. Second thing is that you may wonder why we have tempered representation here. Because only for tempered representation, we can take the integral, direct integral, and let our modules over group polynomial algebra. You know that the group polynomial algebra is highly related to the L2 space, so we have to make sure they are summand of L2 space, so we have tempered representation. You may wonder whether it's a strict condition for the Caspito representation. The answer is no. There's a very famous Ramanujan conjecture says that all Caspito representations are tempered. So if this conjecture is proved, we can just remove this tempered one. Okay, I think that's all I prepared for today's talk. Thank you.